Alright, this video is going to be on drawing. A lot of drawings. Not my forte, but I'll do the best I can. The first drawing I want to do is just generic, sort of show you how waves look or how we represent them. And I'm going to use some words that, I guess not technical, but the correct way of using them. So what I'm drawing now are what are called wave fronts. They're equally spaced. The distance from here to here, you can consider that as your wavelength, and they're moving in a certain direction. I represent that with a ray. So these are the wave fronts, and this is the ray. It has an arrow obviously showing you the direction of it. Some things that can happen to this wave is it could hit a boundary, and we could continue these. Okay, when it hits this boundary, just want to continue till it hits that point. There's a couple things that can happen. It can reflect, which the first thing we do when we have a reflection is draw what's called a normal line. If you remember, normal is a synonym for perpendicular. So this is perpendicular to the boundary. And you can probably guess what's going to happen if it reflects. It's going to go off at whatever angle this is. Maybe I'll change to this color here. Whatever that theta is, that's awful, is going to be the same as this theta coming out. Don't measure it, I'm sure it's not exact, but good enough. And you can also draw the wave fronts going out. Now that's bad right there, and that distance is not the same as all of these. Again, I should be more consistent, just a better drawer, but reflection does not, again, that's not so great. Reflection does not affect the wavelength, so the wavelength should be the same when you go in and when you go out. Some things that kids screw up, actually do this the right way, they measure this as their theta. This is your angle in. It's always measured from normal, so the angle from normal. Same thing with the angle out. It's measured from normal. Sure, this angle here will be the same as this angle here, but that's not the reflected angle. This is the reflected angle. All right, I'm going to erase this and do a couple more drawings. Actually, I'm going to stick with this one and go back to my red color. Actually, I'll change it to blue. If it doesn't reflect, let's say this is light on water, it could also transmit through. And if the medium changes, this is medium 1 and this is medium 2, we get a change in the speed. If you remember, mediums control the speed. So let's say this is fast and this is slow. So when this wave, change it back to red, when this wave enters into this medium, it's going to bend as it changes speed. And in this case, it's going to bend this way, and it's going to bend closer to normal. So this theta here, and I'm going to call this theta refracted, because that's what's happening here. Refraction. Refraction is the bending of the wave as it changes mediums. This will actually be smaller, so theta refracted will be less than theta incident, which is your incoming angle. Okay, I just wanted to get a picture of this. Another thing that changes is if the wave slows down, right? This is the slow medium. The frequency stays the same. If the frequency stays the same, but V is going down, you can imagine what has to happen to lambda. If this is unchanged, this stays, if this slows down, this is unchanged, this has to go with whatever happens to the velocity or the speed. So in this case, it would decrease. So if I were to redraw that, it might look something like that, where you have these condensed waves because they're slowing down. Okay? Trying to think what other things that I can draw. Let's get rid of everything. Erase all the strokes. Last thing that I'll draw is something called diffraction. So we've talked about reflection, refraction, and we're going to talk about diffraction. They all sound similar, but they all are slightly different. If we have a wave traveling, and let's say it comes to a spot, maybe I'll undo that one, comes to a spot where it's not just a boundary. Let's say it's a kind of a barrier with an opening in it. Okay? What those waves are going to do is they are going to spread out like this. And a way that you can envision this is a guy named Huygens, I think he was Danish or Dutch, came up with a way of representing waves as basically wavefronts are made up of all these little tiny wavelets. All right? And all a wavelet is a sort of an individual source of a wave, almost an individual ripple. And what you get when that happens is a wave kind of like fanning out or bending as it goes through an opening, or it could be around an obstacle. All right, picture for this might be, the same thing, but you put a ship right there, and what you'll get is waves filling in around the outside of that. I'll get you a better picture, maybe from the internet, or you can search for one. But this is another form of bending, but it's not due to a change in medium. It's due to an obstacle. That says obstacle. Oh my gosh. Obstacle or opening. And the last thing I'm going to say about this, because I don't want to make the video too long, is the size of the wavelength versus the size of the opening or the obstacle is what's important. If the wavelength is bigger than the opening, then you'll get more diffraction. If it's smaller, you don't. So like a really good example to help you remember this is if you have a light and you put your hand in front of it and it makes a shadow, right? According to diffraction, the light should bend around the obstacle. All right, so you should not get this distinct shadow. The problem is the wavelength of light is on the order of hundreds of nanometers, which is super short. So this idea that the wavelength is bigger than the opening falls apart for light, which is why you see fairly distinct shadows and you don't see bending. But if we have a very small opening or very small objects in front of it, you can see the light bending around it. So I'm going to stop for now.